Okay, this is a video on stoichiometry. Basically, it's a video I'm making for pretty much all classes, just as a review of how stoichiometry works. The reason why I think the video makes a lot of sense is that rather than devote some class time to a topic that you've already learned, I'd rather just give you a video to watch just to refresh your memory. And what should happen is after we watch this video, we're going to do a lab where we do a titration just to review the concepts of stoichiometry through the lab. So this is just meant to be a revisiting. So if you're in my class, obviously you've taken Chem 20 before. We do a big unit on Stoic. So let's just do a quick review about how Stoic works. So generally, stoichiometry follows this sort of pattern. You're going to start with a certain value, like say a liter's number. You'll then multiply it by a moles per liter value, and that should cancel out liters. The thing that makes stoichiometry unique is the next step is almost always a ratio, where what you're trying to do is you're trying to take compound, like say, I don't know, silver nitrate, and that's what you would have started with, silver nitrate, and so that'll cancel that out, and you're going to convert it into copper sulfate, perhaps, and maybe there's like a 2-to-1 ratio. This ratio has to come from an equation, by the way. So you're going to need a balanced equation. The big difference now is the equations we have are going to be based on redox. So that's why we spent the last couple of however long we've been working on redox equations. So last step, and this step really varies again depending on what sort of information you have. You might do something like a grams per mole number. If you do a grams per mole number, it'll give you how many grams you're looking for. Often in a titration, Often in a titration, maybe the best thing to finish with is 1 divided by liters. And the reason why that's useful is now you'll have a moles per liter number, giving you a concentration. Often your job is to look for a concentration of a compound or of a solution of some kind. So one of the most tricky things then that students will have is they got to get it set up. They need to know which number goes here, which number goes here, where the ratio goes, which number goes here. By the way, sometimes this could be a grams and a moles per gram. So you need to have a molar mass. Okay. I would say in my experience, though, most kids, they struggle with getting this liters number and this liters number put in the wrong spots. So one of the reasons why I want to do this video is I think a better investment of time is just to watch a 20-minute video whenever you get a chance. And really, I think you learn stoichiometry and especially titrations just from doing a titration. Hence the lab we're going to do over the next few days. So, but what I do want to do is just 2 examples, just to kind of refresh your memory about how to do a question like this. So I've got 2 examples coming up in a few slides here, and well, why don't we get to them? So here's a slide just talking about what a titration looks like. If you've forgotten, a titration usually involves this long, thin tube, which is called a burette. Let me spell it out for you. This is a burette. And the long, thin tube, basically, it's very precise. It's precise to the nearest 1/10 of a milliliter. So that's 0.1 milliliters. That's how precise it is. And because of that, you're actually allowed to estimate the next digit. So, for example, when you use the burette here, if it measures as like 34.5 milliliters, you can actually figure out whether you think it's 34.50 milliliters or whether you think it's 34.55 milliliters. You can actually figure out whether you think it's halfway in between a marking line. And if you think it's halfway in between, you can go with like 5.5, or if you think it's exactly on, then you can go with 5.0. So, long story short, with that little anecdote, it's a burette is very precise. Okay, accuracy depends on whether it's calibrated or not, and I'll show you the stuff in the lab again in case you've forgotten. We're going to want to put a sample down in the bottom here, and in order to put the sample down here, we typically use a pipette. Because a pipette is also calibrated very precisely. Usually it's calibrated to either 10.00 milliliters, 5.00 milliliters, or I also have some pipettes that do 25.00 milliliters. So you'll pipette a certain amount in the bottom. Then you add the solution drop by drop. And granted, the first time you probably intentionally go too far. and you over add the titrant. The stuff in the burette is, by the way, the titrant. Titrant is the stuff that goes in there. And you hopefully want to go too far, but you just want that as a reference point, because then you want to do it drop by drop by drop once you know approximately how much titrant you need until you get to the drop that causes a color change. Okay, so hopefully that's familiar because you've done this before. Okay, now here's some new information for you, though. Whenever we did titrations in the past, we did acid-base titrations. And using acid-base titrations, you needed to use an indicator. And typically our indicator was phenolphthalein. Close enough. Phenolphthalein. That's not going to work, though, because whenever we do redox work, it may involve acids and base, because many of the equations on our data table involve an H plus or an OH minus, but many of them don't. So we need to try to figure out a way to make this work where there's a distinct color change at the end point. The end point, by the way, is when you stop adding titrant. Typically, the end point is when the pH is 7. But if we don't have pH changing, we need to know when to stop. So we often use one of two different oxidizing agents. We either use this one here, which is a permanganate, or we use this one here, which is a dichromate. And the rationale behind them is we use them because as they react, they change color. We should have done a lab where we were testing out the different strengths of oxidizing agents and reducing agents. And I typically use water, and I use acid, and the other one I use is copper 2+. And as the copper 2+ reacts, it becomes less blue and a little bit more green. That one would work. The only downside to using copper, though, is it's not high enough up on the table. Here's a table. We often use the permanganate or we use the dichromate because they react with almost everybody and they change color. That's the reason we use them. This copper right here is not bad because it's got that blue color to it. The problem is there's too many things that copper doesn't actually react with. But pretty much everybody will react with a permanganate because it's just such a strong oxidizing agent. So, okay, let's do an example. So here's the math we're looking for. Normally, you're going to be given some results in the form of a table. So the first thing you need to do is you need to do some subtracting and figure out how much actual volume was used. So I'm just going to pull up my calculator here. 14.2. And we're going to subtract 2.7. So that's 11.5. And so you guys can do the same sort of thing here. So 25.4 minus 14.2, 11.2. You know what? I can do these in my head. That's 11.1, and that's 11.1. Okay, one of the things that hopefully you'll remember, again, this is a refresher of titrations, is that in order for it to be statistically valid, accurate, which means that hopefully we're using the correct values, we're doing it properly, we want 3 trials within 0.2 milliliters of each other, which means that these 3 trials are valid and this trial is not. And this is what makes titration sometimes take a while, is that it may take you 3 trials, it may take you 7. When I was in university, I had some labs where if I wanted to do really well, because my grade depended on my accuracy, I might do 13 trials. The more trials, hopefully the better, right? So, long story short, it appears that we have an average of 11.1 plus 11.1 plus 11.2, all divided by 3. That's our average volume. And I'm going to use this whole number, so 11.13 repeating is one of my volumes. So there is one volume. And as I scan through the question here, here's another volume. And here is a concentration. So we just got to set this thing up properly. Generally, it looks like this. You need a volume. You need a moles per liter. You need a ratio. And then you need to times by 1 over liters. So let's get the stuff in the right spot. This volume right here is of potassium permanganate. And this concentration right here is also of potassium permanganate. So those are the 2 numbers that can go together. So I'm going to use the 11.13 repeating milliliters. I'm going to start with that. And I'm actually going to cheat. I'm going to use 11.13. I'm going to use milliliters right here. And I'll show you why I can cheat with that in a second here. The next number I need is, this is, by the way, of the potassium permanganate, so I should throw that down there. Then I need its concentration, which is 0.0114 moles per liter. Then I'm going to skip the ratio, and I'm going to throw in my other volume. This volume, 25 milliliters, looks like it's the pipette size, 25 milliliters. And I'm going to write it in as 25.0 milliliters right here. See how I didn't convert to liters? This is just a nifty trick you can play. Because then, rather than canceling this milliliters with that one right there, I'm just going to cancel this one with this one. It's kind of clever. And I'll still have moles per liter when I'm done. The last thing I need to do is I need to find a ratio of KMnO4, which I'm just going to make the MnO4, because really the potassium's not really relevant. Potassium's so low on the list, it's not really applying. And I just got to figure out what MnO4 is reacting with. And if I read carefully, it says it's going to turn chromium 2 into chromium 3. So it looks like it's chromium 2 I need to work with. The question now is, what's my ratio? So I'm going to go to my data booklet and I'm going to try to write an equation, because this is what we've been doing now for the last, I don't know, week, 2 weeks, however long we've been doing this. So I've got this equation up here, and it says I'm using chromium 2+. And so chromium 2+ is right there. Technically, it's also right here, but that's not helpful because I don't want an oxidizing agent. Now's a good time to point out that in order for this to work, the permanganate does need to have H+. So you might see it called acidified permanganate, or it might say somewhere here that it's in an acidic solution. So to write out my equation here, one of the equations is the MnO4 minus aqueous plus, what else do we got here? 8 H pluses plus 5 electrons. And it's going to turn into Mn2+ and 4 waters. Okay, the other equation looks like a chromium 2+ ion is going to go backwards into the chromium 3+ ion. And I can see that right here. It's going back that way, and in doing so, it's going to lose an electron. All right, now we've spent some time working on equations in the past. Hopefully you'll recognize then your next step is we need to times this all by 5 so that these electrons can cancel. Now, I'm not actually going to go through the process of writing this full equation out, because all I care about is my ratio. And my ratio is that I need 1 permanganate for every 5 chromium ions. So we just need to do the math now. I'm going to take 1.13 repeating, which is already in my calculator, times it, wasn't my calculator, times it by 0.0114, times by 5, divide by 1, which I guess I could skip, times by 1, which I guess I could skip, and then divide by 25.0. Here's our answer. Our concentration is 0.025, I gotta check my sig digs here, 25384 moles per liter. Based on sig digs, this gives me 3 sig digs, that gives me 3 sig digs. Oh, it looks like 3 sig digs. So 0.254, 0.0254 moles per liter. And that is the concentration of the chromium ions. And it's the chromium ions because that's the one that didn't cancel here. I didn't actually read the question on the previous slide, but hopefully it says what is the concentration of the chromium ions. So, okay, there's your example. How long did that take? Where is it here? 14 minutes. Okay, so I got 5 minutes left. Let's try one more example. Hopefully that's familiar, because to be perfectly blunt, you've done this before. If I taught you either last year or last semester, I beat your head in with this stuff. We do lots of stoichiometry. For this very reason, I know it's going to come up again. So let's try another example here. This one here says that we actually have to use a primary standard first. So this is a bit of a twist here. On the example we just did, there was a number right here, 0.0114 moles per liter. And I will often say to my students, so you've hopefully heard this before, you cannot trust somebody else's concentration. If they tell you that it's 0.0114 moles per liter, that's no good. You have to make it yourself. And that's actually what this example here is working us through. The number that we're going to need, we're actually going to have to calculate calculate that concentration before we can go forward. So let's start there. We're going to use a primary standard, and basically, if you've forgotten, primary standard refers to a solid that we can weigh on a scale. So I'm going to take 1.87 grams. I'm going to use a mole per gram. That's a molar mass. I'll find that in a second. And since we made it in a 100 milliliter volumetric flask, I'm going to times by 1 divided by 0.100 liters. And this will give us the concentration which we made ourselves. And when you guys do your lab on Monday, same thing. I'm not going to let you cut corners. I'm not going to give you a solution and say, hey, here's the concentration. You need to make the solution yourself. So, okay, so the piece of information we're lacking is the molar mass. And I do this example on purpose because the primary standard that we use is this absolutely insane compound. So if you take a look at it, it's called an iron 2 ammonia sulfate heptahydrate. And the reason we use it is because it has probably one of the most accurate molar masses because of the fact that it's so heavy. There's so much stuff compacted in there that we actually are fairly certain of its molar mass as opposed to something that was only quite small. You'd never be expected to name this one, but this is the one we're going to use in our lab on Monday. So we got to find its molar mass, which is pretty insane because you're going to need to do iron, which is 5585, and we'll have to times that. No, you just need one of them. You'll need nitrogen, which is 1401, and you'll need 2 of them. You'll need hydrogen, which is 101, and you're going to need 8 plus 12 more, so you're going to need 20. You're going to need sulfur, which is 3207, and you'll need 2 of them. And you're going to need oxygen, which is 16, and you need 8 and 6 more, so you need 14. 8 and 6. Yeah, 14. Okay, calculator, help me out here. So I need a 5585, 1401 times 2, a 101 times 20, a 3207 times 2, and 16 times 14. So this guy's got a pretty crazy, insane molar mass, but hopefully it's 392.21. I really hope I don't screw up that number. 392.21. Just centering the screen again here. Okay, 392.21. Again, the reason why we use that compound is its molar mass is so large that we hopefully are fairly confident in it because it's a large number. That helps. It gives us a lot of sig digs. And I guess one more reason, if it's got a large molar mass, we don't have to use as much of it. So, okay, so let's do this math here. I guess I need my calculator out again. I need 1.87. I need to divide by that molar mass, and I have to divide by 0.100. So I've now made a concentration. I'm going to, in my calculator, store that as answer A. So it's A moles per liter, which is 0.0476, basically. So hopefully that makes sense so far. So this is a solution we made ourselves. Okay. Now, what happens if you read through this scenario, and this is kind of similar to the one we're going to do, is we're going to use a solution we made of iron 2. It's actually the iron 2 that really matters. It's the Fe2 plus that's going to be there. And we're going to use it to titrate 10 milliliters of potassium dichromate. This helps us find the potassium dichromate's concentration, but we actually don't care about the potassium dichromate's concentration. What we actually want is to find a tin concentration. So this is kind of a complicated scenario where you're not going to do this on the diploma, but we actually have to do a titration using one solution to find a second solution, only to use that second solution and find a third solution. So it ends up being kind of a lot of work. So I may end up going over my 20-minute limit here. It might be closer to 30, but let's walk through it. So here's some more charts. Basically 2 different titrations, and we'll use them as we need to, but let's just do the math for the volume. This is going to be 11.3. That one's going to be 11.3? Yeah. That one's going to be 11.0. That'll be 11.1 and 11.0. So I can average those 3. So what's that going to be? 11.03 repeated, I think. Let's double check. 11 plus 11 plus 11.1. Yeah, 11.03 repeating. And then we're actually doing 2 titrations. So we're going to make a solution, titrate it to find a middle solution, use that solution to find a next solution. So for this one here, same sort of concept. Need to subtract these, so that's going to be what, 10 point. Let's see, 10.4. Oh my gosh, I can't do math. No, 10.8. What's that going to be? 10.5. 10.5. 10.5, I think. Hopefully I didn't screw that up. All right, so I think that one averages to 10.5 milliliters. I think so. Embarrassing if it's not. Okay, so let's set this up here. What we're going to do is we're going to take the iron solution that we made, and we're going to use it to titrate a dichromate. So we have a concentration of this guy because we made it. We're going to use it to titrate a dichromate so that we know the dichromate's concentration. And then we're going to use the dichromate to titrate tin 2. Oops, went too far. We're going to use the dichromate to titrate tin 2 so that we can find this guy's concentration. Okay, you might be asking, Chris, why would we go through all the work to do that? And the reason why is that I can't directly go from iron to tin because there's no color change. And so if there's no color change, it's no good, because how do I know when to stop the titration? So I could try titrating iron and tin together. It totally will work, but I'll never know when to stop my titration. So this is why I need the go-between. I'm going to take iron and titrate it with dichromate, because dichromate will change color. And then once I know the dichromate, I'll titrate it with tin. Okay, so let's do the work. We're going to start with a liters. We're going to do a moles per liter. We're then going to do a ratio. And then we're going to do a 1 divided by liters. And we're going to start with iron 2+. And we're going to bridge it in the middle with the dichromate. So let's fill in what numbers we can. So first I got to figure out how many liters of iron was used. And as I read this chart right here and this chart right here, those are about the dichromate, so that's not it. The dichromate is what's in the burette. So it actually says that I used 10 milliliters. So I'm going to start there. We used 10 milliliters. The concentration, I'm just going to put down capital letter A because I've already stored that in my calculator. Because again, we made it from scratch. Then when I'm looking for the dichromate volume then comes out of the chart, which is 11.03 repeated. And again, I'm going to play that little cheat here. I'm going to cancel this milliliters with that milliliters so that I can get the concentration. What this will do is it'll give me the concentration in moles per liter of the dichromate. I'm just lacking one thing. The thing I'm lacking is the ratio. Sometimes you can cheat with the ratio and just figure out what the electron balance happens to be. The dichromate reaction needs 6 electrons, whereas iron 2+ needs 1 electron. So once you figure out that it's this dichromate reacting with this iron right here, well, I mean, at that point there, basically, you just need to figure out the ratio. It's 1 to 6, so you're going to need 6 irons for every 1 dichromate. So there, that's the information I need. Where are we here? There it is. 6 no, not 6 dichromates. 1 dichromate for every 6 irons. So let me recap here. 10 milliliters of iron was used. It was used in a pipette. We know its concentration because we made this. We then know the ratio of iron to dichromate, and then the amount of dichromate used comes out of the chart because this was in the burette. Now, unfortunately, we're not done because dichromate is just a go-between. Again, the reason why is that I'd love to go directly from iron to tin. My goal is to find tin. But iron does not change color, neither does tin. So I'm going to use dichromate, which does change color, hence can be done a titration with. And so now I have to actually do the second step. Now I'm going to leave the math for you guys to do here. But this is going to give you a concentration of dichromate, and I'm just going to call it letter B for right now. And I'll assume that you guys can handle putting stuff in your calculator. Because then we do the exact same thing. We now are going to take a certain volume in milliliters of dichromate, and in a second set of titrations, we're going to times by its concentration. We're going to use its ratio, and we'll do 1 divided by liters. Only this time around, we are now getting rid of the dichromate number, and we're trying to get to tin 2+, because ultimately that's what we were looking for. We were looking for the concentration of tin 2+. Again, the most common mistake kids make is they put their volumes in the wrong spots. So I need to know the volume of dichromate used. And that's actually why we have a second chart, because this is a chart, again, for how much dichromate is used. So it was 10.5 milliliters in the second set of titrations. Fortunately, we now know dichromate's concentration because we just found it. So whatever you get for B, that's going to go right here. We need to know the ratio of tin 2 to dichromate. So I'm just going to kind of cheat a little bit here and just find them in the data booklet. Dichromate is up here with its 6 electrons. Tin is right here with its 2 electrons. So how do you balance a 2 and a 6? Well, these guys need to be times by 3, basically, times by 3. So you need 3 tins. Where's that work I had? We need 3 tins for every 1 dichromate. Okay, last thing, we then need to know how many milliliters of tin were used. And it actually said that on the first slide. We used 10 milliliters of tin, the rationale being that's the size of the pipette we used. So I'm just going to, again, cheat, and I'll just use 10 milliliters because this milliliters and that milliliters will cancel. And that'll get us our answer. So I'm going to skip the calculator portion just to save you some time, but that is now our moles per liter of tin. So quick recap. Hopefully the work that you currently see on the screen is not foreign to you. If not, you need to really brush up on how stoichiometry principles and titrations work. The biggest struggle is probably interpreting where all the numbers are coming from and just keeping them straight. So like I said, the best way of doing this is probably to actually do it. Rather than talk about it on paper, we're going to do a lab. So the next couple of days, whenever it's scheduled in the schedule, we're going to do a 2-day lab where first you guys are going to make an iron solution. Then you're going to titrate the iron solution that you made with, we actually use permanganate rather than dichromate because the permanganate does the nice purple to clear color thing. So it functions like phenolphthalein. It's clear and then it turns just the faintest pink. We use the go-between because it changes color. And then we use the go-between to then solve for what we're actually looking for. What we're going to do in our lab will look like this. We're going to make a solution of iron. we're going to use iron to try to calculate a concentration of permanganate, and then we use the permanganate to calculate the concentration of peroxide. On the bottle, hydrogen peroxide claims that is 3% weight by volume. We're going to test that claim. It's very similar to a lab you would have done in grade 11, where we tested to see whether acetic acid was 5% weight by volume. So hopefully whoever we buy the peroxide from is actually telling the truth about it being 3%. Often when my kids do this, they're often very close. Like it's nearly 100% correct. Like the percent difference is 5%, 3%. So, okay, that's the tutorial. Hopefully that was mostly a review. If you didn't need to watch that all, that's fantastic. But if you stuck it out to the end of the lesson, thanks for watching. And when I see you guys again next, then we'll actually do these titrations. So print off the lab. Okay, we'll see you guys later.